In this video, we're going to look at all the different types of stereoisomers. So stereoisomers are compounds that have the same molecular bonds in the same order, but the atoms are arranged differently in space. So there are two different types. There's configurational isomers and conformational isomers. Configurational isomers cannot be converted by rotations about single bonds. So those are either cis and trans and EZ isomers. So they're compounds that have different arrangements around a central atom, but there's restricted rotations. And then there's optical isomers, which are mirror images that show chirality, which we'll talk about too. Conformational isomers, which is the first one we'll look at, are compounds that can be converted just by rotating about the single bond. So these ones are the easiest to convert back to, like switch between one and the other. So a conformational isomer are isomers that are able to rotate on their sigma bonds to interconvert between one another. So an example would be ethane. So one conformation is the staggered conformer. So everything is just offset, like so. So this is the top carbon, and then underneath is the bottom carbon. So they're all offset. Whereas an eclipse conformer, they've been rotated onto themselves, so now the hydrogens are all layering right on top of each other. But so this example is ethane, the one that we're looking at. One of the conformations is staggered, one's eclipsed, and they can easily convert back and forth because you can just spin around that single sigma bond, but also the energy difference is so minimal that it's very easy to alternate back and forth. So cis-trans isomers, so this would be seen in alkenes and cyclic molecules where there isn't free rotation around the bond anymore, so it's limited motion. So in this case, you'll end up with cis-trans isomers. And the only way you can interconvert them is to break the double bond and actually rotate and then reform the double bond, so this doesn't happen so often. So in this example, so we have butene. So there's a carbon, another carbon, the double bond to the carbon to another carbon. So the way I remember cis and trans, cis looks like a C. So the two hydrogens are both on the same side of the double bond. So it's C. Whereas trans isomers, the hydrogens are on opposite. So it's like going across the Trans-Canada Highway. So they're across the double bond. So the first one is cis-butene and the other one is trans-butene. So we look at another example. In this one, this is ethene, but it's dichloroethene. In this one, the cis conformation, so this one, both of the chlorines are on the same side of the double bond, which will cause them to have a more negative dipole than the other side. So this makes the molecule polar and has a higher boiling point than the trans configuration because they're across the double bond, making it non-polar and have a lower boiling point. So cyclic molecules also undergo cis-trans isomerism because they aren't free to rotate around their bonds either because they're all joined to one another. So this would be how you would represent the cis 1,3-dichlorobutane. So the chlorines are both pointing downwards. And the trans configuration, one is pointing up and one is pointing down. So sometimes you have more than just two different groups attached to each carbon in the double bond. So then you have to name them as EZ isomers. So to name them, you need to apply something known as the Kohn-Ingold Prelog priority rules, or CIP rules. It's named after the scientist that came up with the naming system. So what they decided was that you'll assign priority to each atom on the carbon by their atomic number. So if the high priority atoms are on the same side, then it's the Z isomer for zusammen, or together in German. And if the high priority atoms are on the opposite sides of the double bond, then they're the E isomer. So entgegen, or opposite in German. So we'll go through some examples. Okay, so we'll look at this first example. So in this one we have ethene that's been substituted with a chlorine, a fluorine, a bromine, and a hydrogen. So we'll look at the two separately. So we use the atomic number as the priority. So on carbon number 1, chlorine has the higher priority because it has the higher atomic number, and bromine has the higher priority on the second carbon because it's got a higher atomic number than hydrogen. So this one is going to be the Z isomer. So we're going to name it as such. Z, and then it's 2-bromo. Remember, we name these in alphabetical order. 1-chloro, 1-fluoro, ethene. So sometimes we have to look at what the groups are. So if it's not a halogen that's attached, but it's another alkyl group, so we need to find the one that has the most priority. So this carbon, on the second carbon, is bonded to a methane and then an ethyl group, an ethane. So this one has a higher priority because it's bonded to 2 hydrogens and a carbon, where this one's only bonded to 3 hydrogens. So this one would be the high priority, and we would name as such. So we would assign priority. So chlorine has a higher atomic number than fluorine, so we would circle it. And then this one, as I've already mentioned, has the higher priority. So this would be the Z configuration. And this one here, so chlorine, but then this one, so this is the E isomer. Our next type of isomer are optical isomers. So this happens in chiral molecules. And chiral molecules are molecules that have a carbon. So a chiral carbon has 4 different things bonded to it. So the chiral carbon is then said to be asymmetric because it doesn't have symmetry on any of the bonding groups. And chiral carbons cause 2 enantiomers, which are mirror image isomers. So you can see here that we've got this group, and then this is pointing to the right, this one's pointing to the left, this is to the right, this is to the left, and this one's kind of pointing down to the right and down to the left. So they're mirror images of one another. So because the 2 isomers are mirror images of one another, they're not superimposable. Just like 2 hands, you can't lay your left hand on top of your right hand, pointing upwards, both of them, and have them superimpose. So they do have the same physical properties, chiral compounds, just like our hands both have different physical properties, but the chiral compounds, their chemical properties can be different. So that can be a problem sometimes. So those 2 enantiomers are said to be optically active, which means that if you pass plain polarized light through a tube that contains some of the enantiomer, one of the enantiomers will rotate that plain polarized light clockwise, and the other one will rotate it anti-clockwise. However, in a racemic mixture, you have equal amounts of the 2 enantiomers, which will make the solution optically inactive. So when you send polarized light through that solution, then there isn't that rotation because they equally cancel each other out. So there's no overall rotation. So those types of solutions are considered optically inactive. So if we go back to our SN1 and SN2 reactions, we were told that SN1 reactions start with a single enantiomer and they end up with a racemic mixture of 2 enantiomers. So that makes the mixture optically inactive. However, SN2 reactions start and end with only one enantiomer, so the final product is optically active. Our final concept is diastereomers. So when there's more than one chirocarbon in a molecule, you can form enantiomers, which are mirror images of one another, but you can also form diastereomers, which are not mirror images of one another. So they are not superimposable either.